Hi, welcome to our first lecture on complex numbers. Now, what is a complex number? A complex number, right, is a number that has two components to it. One is the real component, the other is the imaginary component. Okay, real numbers are what we know. It could be pure integer numbers, could be 1, 5, or it could be decimal numbers 3.2, 4.17, and so on. So these are all examples of real numbers. But what are imaginary numbers? Okay, to understand the concept of imaginary numbers, let's go back a bit and look back at the square root of a number. Now, when I give you a number, let's say 16, and ask you to square root it, mathematically the answer must always be written as plus minus. In this case, the answer will be 4. Alright, why do we write as plus minus 4? Because we know that positive 4, okay, multiplied by positive 4 would give me 16. Alright, or in other words positive 16, which is what we have here. The other way in which I can get positive 16 is I take negative 4 multiplied by negative 4, and in this case I will also get positive 16. So as you can see, whenever I square root a number, I will always get some answer, but I must put a plus or minus in front, because positive times positive will give me positive, and negative times negative will give me positive. Now, how about having a negative, a square root of a negative number? How is that possible? Okay, as you can see here, when I do a square operation, which is opposite of square root, both the numbers must be the same. So it has to be positive 4 and positive 4, or negative 4 and negative 4. And in both these cases, the answer is always going to be positive. Okay, the answer is always going to be positive, because positive times positive is positive, negative times negative is also positive. Alright, so I will always end up with a positive answer here. But if I were to square root a negative number, I am trying to get two numbers, okay, maybe a multiplied by a. Okay, two numbers has to be the same, correct, where the result is negative. And we know that this is actually not possible with our real numbers, right? Because for real numbers, when both the numbers are the same and I multiply them, either they are both positive or they are both negative, and in both cases, all right, the answer would be a positive only. So when I try to do a square root of a negative number, it's actually not possible. Okay, if you try to key in your calculator, you will not be able to get a answer. So that leads us to understanding the idea of creating this new domain called the imaginary number. Alright, so in this complex domain, we now have real numbers and imaginary numbers, and the baseline imaginary number is what we call the square root of a negative 1, and this is normally represented in most resources as either I or J. Okay, in most online resources or textbooks that you refer to, square root of negative 1 is represented as I or J. Now, how do we write a full complex number? As I just told you just now, complex number is consists of both a real part and an imaginary part, and that is written as, okay, x plus jy, Okay, in some cases it could be a plus I b and so on. All right, so as you can see, there are two parts to it. The first part of the number, or the number without the I or the j, that is what we call the real part of the number. Okay, the second part is the number with the I or a j, and that is the imaginary part of the number. Okay, the imaginary part of the number. You can also represent complex numbers in the graphical form. To do that, first we're going to draw the axis here. Now, the x-axis will be used to represent the real numbers, while the y-axis represents the imaginary numbers. Okay, and if I have a complex number that is something like this, 3 plus j4, this is the real part. That means on the x-axis I look at a value 3, and j4, this 4 is the imaginary part. Alright, so on the y-axis, which is imaginary, I look for a value 4. Alright, and the point where they both meet, okay, I can draw a vector to that point, and that represents this complex number here, 3 plus j4. Alright, so now what we have is we have gotten a good overview of some complex number terminology. Now let's move on to understand the basic operations that we can actually do with complex numbers. The first is addition and subtraction. So addition and subtraction. Given any two complex numbers, okay, a plus jb, add with c plus jd, the way we perform complex number addition or subtraction is to basically focus on the real numbers separately and the complex numbers separately. Okay, so in this case you have a and c as the real parts of the number, b and d as the imaginary parts of the number. So that will bring us to a plus c, add with j, b plus d. Okay, now let's try an example here. 3 plus 2j, add with 1 plus 7j. So in order for us to perform this addition, the real parts will be added together and the complex parts will be added together. So what you have is 3 plus 1, add with j2 plus 7, and that will give us 4 plus j9. That is the final answer here. Let's try another example. 3 plus j5, add with 4 minus 3j. So again, the real parts will be done separately and the imaginary parts will be done separately. So what I have here is 3 plus 4, add with j5 minus 3. and I will get 7 plus j2. Now let's just understand how I can also perform such addition or subtraction operations in the graphical or using the graphical approach. Okay, let me draw the axis here. So here I have the y-axis and here I have the x-axis. So this would be the real part and here will be imaginary part. The first number is 3 plus j5. So 3 here and 5 here. Alright, I will get a vector that goes up in that direction. And this complex number is now going to be added with another complex number here. Right. So though I use the term vector because it can be represented, okay, in a similar way like how we do a vector addition and subtraction. Okay, so when we study vectors, we know that vectors can also be drawn graphically and solved graphically, so that same approach can also be used here. Okay, so that is why I use the term vectors, all right, in this class. Now the second complex number, all right, is 4 minus 3j. Now since it is one complex number add with another complex number, this second number, all right, will then will be extended from where the first complex number left off. So the first complex number ended at this point here. So from this point I will go 4 units in the real axis. So 3 plus 4 would be 7. So I'll go here 4 units, and then I will need to go down 3 units in the imaginary axis. So go down 3 units. So 5 minus 3 would be 2. So it will be somewhere here. So the new position of my vector addition would be this point here. And since there's no other addition involved, the final answer is actually from here to this point here, which is 7, okay, plus 2j, okay, which is what we have here. Alright, so what I've shown you is how you can apply the vector approach, alright, to solving complex numbers in a graphical form. Of course, it is very tedious to keep drawing and solving such operations. So the more straightforward algebraic approach is a lot faster and easier. Okay, now let's look at a few more examples. The next question I'm going to look at is this: minus 4 plus 7i plus 5 minus 10i. Okay, so let's look at how we can do this. So the first step is we want to open up all the brackets right now. Okay, so in the first two examples here, I straight away looked at real numbers and complex numbers. Okay, and that approach is easy and straightforward as long as the sign, okay, in front of the complex numbers is positive. Okay, the moment you have a negative sign, things will change. All right, so in order for us to make sure that we always do it correctly, I'm going to show you the better way of approaching these addition and subtraction operations, which is to first open up all the brackets. Okay, first open up all the brackets and then we look at the real numbers and the imaginary numbers. Okay, so let me repeat that. The better approach, all right, would be to always open up all the brackets first and then look at the real numbers and then the imaginary numbers. So I'm going to open up all the brackets first. So I'll have negative 4, okay, plus 7i. For this bracket, since the sign outside is positive, nothing changes because positive times positive is still positive and positive times negative is negative. Okay, so the real parts are here and the imaginary parts are here. So the next step is minus 4 plus 5 plus I 7 minus 10. Okay, and that would give me 1 minus 3i. That is the final answer here. Okay, so when you write complex numbers, you can write the I or j before the number or after the number. Doesn't matter, both are the same. Alright, let's look at another example now. 4 plus 12i minus 3 minus 15i. Now, in this example, you will see more clearly why I say opening up the bracket is very, very important. Because when you have a negative sign in front of a bracket, all the signs within the bracket will change once you open up the bracket. Okay, so for the first bracket here, there is no change. 4 plus 12i. Now for the second bracket, what you're going to have is, you will see that negative times positive will give me a negative 3, and negative times a negative would give me a positive 15i. So as you can see, now the signs have changed. Alright, that is why it's very important to open up all the brackets first. Okay, open up all the brackets first before you group up the real numbers and the imaginary numbers. So for the real parts, I have this and this, and for the imaginary parts, I have this and this. Okay, so I have 4 minus 3 plus I 12 plus 15, which will give me 1 plus I 27. Okay, now let's look at another example here. 5i minus 9 plus I. So we're going to follow the same process. For the first complex number here, there is only the imaginary part, there is no real part. So that will remain as it is. Now, when I open up the bracket, negative times negative will give me positive 9, and negative times positive will give me negative I. Okay, so now I only have one real part and two imaginary parts here. So the next step would be to group them together. So real part is only 1 plus 5 minus 1i, which will give me 9 plus 4i. Okay, let's try another example here. 4 plus j1 minus 2 plus j3. Let's follow the same process. The first bracket, there is no issue because the sign outside is positive. So 4 plus j1. Now for here, I multiply inside. So minus 2, negative and positive is negative j3. So the real numbers are 4 and minus 2. The imaginary numbers are plus j1 and negative j3. So what I have is 4 minus 2 plus j1 minus 3. So the final answer would be 2 minus j2. So that wraps up the addition and subtraction part of the complex number operations. Right now, let's move on to multiplication. Now, for multiplication, you're talking about multiplying two complex numbers while they are in this current form of a plus jb. Okay, so I have two complex numbers. The first one is a plus jb, and the second one is another complex number, c plus jd. And how will I perform the multiplication here? To do this, you follow the same approach as how you would perform the expansion of two uh, normal algebra expressions. For example, if I give you 2x plus 3, okay, and the second expression as x plus 2, how would you do this or perform this expansion here? Okay, to perform this expansion, you would have done the uh, approach where you take first term multiplied by first term, so I got 2x squared, first term multiplied by second term, so I get 4x, second term multiplied by first term plus 3x, and second term multiplied by second term plus 6. And then what would we have done? We would have grouped them together. So x squared is only 1. There are two x terms, so it will be 7x, and then there's one more term here, a constant. Alright, so this is how we would have done a normal expansion, okay, with algebra principles. We are now going to apply the same approach to complex numbers. Okay, so first will be a multiplied by c, I get ac. A multiplied by jd, I get j a d. jb multiplied by c, I get jbc, plus jb multiplied by jd, I get j square bd. Okay, next we do the same approach where we group the similar terms together. So I'll have ac plus j ad plus bc, and you have this j square bd over here. Now this is something new that we're going to deal with. What is j square? Now let's come and explore this a bit. We know that j is square root of minus 1. So j square is j multiplied by j, which is square root minus 1 times square root minus 1. Okay, now we're going to apply the indices approach here, where my square root we know is minus 1 to the power of half multiplied by minus 1 to the power of half. Alright, and by indices rule, we will now be able to add the powers together. Okay, why? Because the indices rule says that am times an is equals to am plus n. So here I have half plus half, and that would give me minus 1 to the power of 1, which is minus 1. Okay, so what I've tried to show you is the sort of derivation, but whatever the case, the important point here is that j square equals to minus 1. Alright, this is the important takeaway from this derivation. Now with that, what happens here? Okay, coming back to our multiplication here, this j square will now be a minus 1. So this becomes minus bd. And what do you see here? You see that now this term here, this negative bd, is no longer a imaginary number because there is no j associated with it anymore. It is now a real number just like AC. Alright, so that means that I can now group AC together with BD, and this is another group here, JD, AD plus BC. So what we have now is this representing the real part and this representing the imaginary part. Okay, so after you do the multiplication, this is your you will derive or you will arrive at a final answer that consists of a real part and an imaginary part here. Now let's try it out, okay, and see how it works. Okay, so let's try this example here. 3 plus 2i multiplied by 1 plus 7i. Okay, so what we're going to do is we're going to do the same approach here where we're going to expand. So 3 times 1, so 3 multiplied by 1 plus 3 multiplied by 7i plus 2i multiplied by 1 plus 2i multiplied by 7i. And what do you get? 3 plus 21i plus 2i plus 14i squared. Okay, and then 3 plus, so this I and I, they are both imaginary numbers, so they can be combined together. And I square, we just saw it is minus 1, so you can just, if you want to be very sure you don't make any mistakes with the plus and minus, you can put the minus 1 first in a bracket, okay, and then you open up the bracket. So why I say this is a good approach is because if this sign was a negative, then again things would change. All right, but now it is a positive, so 3 plus 23i plus and minus will be minus 14. So what I have is minus 11 plus 23i. Okay, so that is the final answer for this complex number multiplication. Let's try a few more examples. 7i multiplied by minus 5 plus 2i. Now in this example, what you have is you do not have a complete complex number, you only have the imaginary part multiplied into a full complex number here. But the same rules apply. Okay, just imagine that you have a algebra expression 2 plus 2 into 5 plus 2x. What would we do? We would do the normal expansion. 2 plus 5, which is 10, plus 4x. Alright, so the same approach is what we're going to do here. So 7i times minus 5, so I'm going to write that here, 7i times minus 5 followed by plus 7i times 2i. Okay, 7i times negative 5 will be negative 35i plus 7 times 2 is 14i squared. Okay, and as I said, this is minus 35. I square is minus 1, so I'm going to put a minus 1 here. 14. So this would be negative 35i negative 14. Alright, generally when we write the answer of a complex number, we write the real part first, followed by the imaginary part. So that is the final answer here. Let's try another sum now. 1 minus 5i multiplied into minus 9 plus 2i. So we're going to take the same approach. Okay, we're going to do the expansion first. Okay, 1 times minus 9 plus 1 into 2i plus negative 5i and negative 9 plus negative 5i and 2i. Okay, so what I have next is 1 times minus 9 is minus 9 plus 2i plus negative 5 times negative 9 is 45i, negative 10i squared. Okay, then we're going to group them up. So negative 9 plus 47i, I square is minus 1, so negative 1 into 10. So this is what I mentioned just now, where if you have a negative sign in front, okay, it's good to put the bracket so that when you open up you get the correct sign. Minus 9 plus 47i plus 10, okay, which gives us 1 plus 47i. Okay, now let's go on to another question. 4 plus I multiplied into 2 plus 3i. Okay, let's do the expansion. 4 into 2. So now I'm not going to write all the brackets. I'm going to straight away do the multiplication. 4 times 2 will be 8 plus 12i plus 2i plus 3i squared. And by doing the grouping, I get 8 plus 14i. I square is minus 1, so minus 3. And finally, I'll get 5 plus 14i. Okay, now let's do one more example here. 1 minus 8i multiplied into 1 plus 8i. Okay, so this is a bit interesting. Let's expand and see what happens here. So 1 into 1, I get 1. 1 plus 8i is 1 is 8i. 1 multiplied by plus 8i is 8i. Minus 8i multiplied by 1 is minus 8i. And minus 8i multiplied by positive 8i is minus 64i squared. Okay, now what do you see here? You see that I have 1 positive 8i and negative 8i. When you group them together, they actually become 0. Correct? They cancel each other out. So the left is minus 64i squared. Right? So minus I square is minus 1 and 64. So I get 1 plus 64, which is 65. So here you can see that when I have two complex numbers multiplied by each other, okay, where one is the conjugate of the other. Okay, so this is what we call a complex conjugate, where the complex numbers are the same except that the imaginary parts have opposite signs. Alright, so one is 1 negative 8i, the other is 1 plus 8i. So they are exactly the same except that the signs are different. Okay, and when you multiply two complex numbers together, where one is the complex conjugate of the other, the result, as you can see, is just a real number. There is no imaginary part to this. Okay, and this is an interesting and important technique that you will actually be using in the next part, which is division. Okay, so let's move on to division. Okay, now for division, okay, division, we are going to see how we can approach division with complex numbers in its current form. So let's look at this example here. 3 minus I divided by 2 plus 7I. Okay, the way we can approach division, okay, of complex numbers is by using what I just talked to you about, the complex conjugate. Because what we saw just now was that when I multiply a complex number by its complex conjugate, what I have as a result is a real number without the imaginary portion anymore. Alright, so that is the direction we must take to perform division of complex numbers, where we want to eliminate the imaginary part in the denominator. So what I need to do is multiply both the numerator and denominator by the complex conjugate of the denominator. So I will multiply them by 2 minus 7I divided by 2 minus 7I. Okay, so the denominator of the question here is 2 plus 7I. The complex conjugate is 2 minus 7I. Okay, and when I multiply it by 2 minus 7I over 2 minus 7I, nothing changes because they are both the same, so it's equivalent to 1 over 1, correct? So nothing changes, but as a result of this operation, what would happen is the denominator, as you can see, is the multiplication of a complex number with its conjugate, which means that after I complete this operation, the denominator will only have a real part to it without the imaginary part. Okay, so let's see that and understand how this works. Okay, so I'm going to write it as a single fraction. 3 minus I, 2 minus 7I, 2 plus 7I, and 2 minus 7I. Okay, so for the top part here, 3 times 2, which is 6, minus 21I minus 2I. Okay, minus the minus is plus 7I squared, and the denominator is 2 into 2 is 4, negative 14I, 7 and 2 is plus 14I, and negative 49I squared. Okay, let's carry on. So at the top, what you have is 6 minus 23I. I square is minus 1, so plus minus 1 into 7. In the denominator, you have both the items cancelling each other out, so you have 4 minus I square is minus 1 into 49. Okay, so what you have next is, okay, so at the top we have 6 minus 23I minus 7. At the denominator, what we have is 4 plus 49. Okay, so we have minus 1 minus 23I over 53. Okay, normally what how we will write it is as minus 1 over 53 minus 23 over 53I. Okay, so that is the final answer here for this complex number division. All right, it does seem a bit long-winded, okay, but with complex numbers in this current form, this is the way you must do division. All right, where you start off with the complex conjugate, and then with that your denominator becomes a single number, a real number without the imaginary part, and from there you perform the necessary algebra operations to derive at the final answer here. Okay, so let's just try one more question. Okay, 3 minus 3 divided by 9 minus I. Okay, so the way to do it, first step is we multiply both the numerator and denominator by the complex conjugate. The complex conjugate of the denominator is 9 minus I, so the complex conjugate is 9 plus I divided by 9 plus I. Okay, so that gives us 3 into 9 plus I, and the denominator you have 9 minus I and 9 plus I. Okay, what you have next is on the top you have 27 plus 3I divided by, okay, after a while you will get used to the idea that complex number conjugate multiplications will not have the item, so I can just focus on the real number and real number, okay, and the imaginary number and imaginary number minus I squared. Okay, so next what I have is 27 plus 3I divided by 81. I square is minus 1, so minus or minus is plus 1. Okay, so equals to 27 plus 3I over 82, and that will be written as 27 over 82 plus 3 over 82I. Okay, and that is the final answer for this complex number division here. Okay, so I hope that with this lesson you have gotten a good understanding of how to approach complex numbers and some basic arithmetic in its current form. In subsequent videos, we'll be looking at other ways of representing complex numbers and how we can perform similar operations when they are in those different forms. Alright, thank you very much, and I'll see you soon in the next video. Bye.